Hi everyone, my name is Anshul and I'm making this video about the uses of predictive analytics in education for the MS and PhD students in health professions education at the MGH Institute of Health Professions. So we'll get started. Here's a little bit of information about this presentation. Most notably, you can get these slides at this link right here. And then remember, you can pause the video anytime you'd like if there's something you'd like to look at for longer. So our goals are to see an example using real data of how analytic methods can help us as educators. So I'll start with a silly example that I like. Imagine you've made spaghetti, and so in your cooking pot, you've got some spaghetti and some water, and you need to separate them. So what you'll probably use is some kind of filter or colander, right, to pour everything in, and that'll separate the spaghetti from the water. And in machine learning terms or predictive analytic terms, what we're doing in that situation is we're separating or classifying the spaghetti and the water into two separate groups. And so what we'll be doing in this example today is not that different. You can imagine you're actually going to be pouring students into a filter and then see who gets caught as students who need additional support and see which students don't get caught as students who are not considered to be at risk of potentially failing a course or some other educational degree evaluation or assessment. So this is the information about the data used in this example and where you can get it from. So if you would like to do that, then you can follow these links displayed here. Okay, so what's our goal? Our goal is to imagine that we're instructors, educators in some kind of large course with a lot of students or a large educational program. And our goal is to improve our student outcomes and support our students better. So I know that's vague, but we're going to make it more specific as we go. But what I want to do first is show you the data that we have. And so we'll actually go to the data and have a look now. So what we have in this case is example of 649 students from Portugal. And this is real data collected from two schools. And we have all the information here that you see across the top from these students. And what we're going to do is call this last year's data. So this is the information of the students as well as their academic results from 1 year ago. And so we have demographic information about all the students, as you can see as the headers at the top here. And then if you go to the right, we have G1, which is their grade at the midterm of the semester. G2 is another midterm grade. And G3 is their final grade in the class. And so I'll move over a little. And so if you scored less than 10 on your final grade, as this person here in row 20 did, and as many others did later on in the data set, let's go down. Here we go. See more people who scored less than 10. If you scored less than 10, then you failed the class. And so what we want to do is prevent people this year from failing the class in as many numbers as people did last year. So that's our goal. And now let's look at what this year's data looks like. So what this year's data looks like is here in this tab. And so again, this year, imagine we have a new set of students and we can collect all of the same demographic information about this year's new students and we can put them in a spreadsheet just like this. And this is an example of what it would look like. And then if we move over though, we see that we don't know people's final grades yet. So we're imagining that we've started the semester and we do know midterm grade number 1, G1, for this year's new students, but we don't know their final grade. But imagine if we could use all of the data I've just shown you to create some kind of sorting mechanism, just like this. Then what we could do is we could actually predict which students are at risk of failing this year's class, and we could fill in these question marks that you see here. So that's our goal to keep in mind for the rest of the video. So we'll come back here. Just another thing to note, last year's students were 649 in total number. And just a reminder that if you scored 10 or above, that meant you passed. Okay, so we're going to take a minute here to look at a roadmap of our entire process that we're going to follow to answer the question I just described for you. We're going to start with last year's data. We're going to take 75% of it, and we're going to train some kind of predictive machine learning model, which again is just a fancy filter inside of the computer. And then we're going to take 25% of last year's data, and we're going to test how good is that filter we just made. If we trust that that filter we just made is a good filter, then we'll put this year's data through that filter and try to figure out, okay, which students are at risk this year of failing the class. So I know this is maybe a complicated flowchart, but we'll go through the components of it in the rest of the presentation. So now we can make our goal more specific. We know that last year, 100 students failed and 549 passed. And we also know that those students, demographic information, their midterm information, and we also know their final grades. Knowing all of that, can we reduce this year's number of students who fail the class? Okay, so this is a summary of all of the variables, which were each of the columns of data in the Excel sheet that you can still see a glimpse of on your right. So you can read through this in more detail if you'd like. This is also in the paper that's cited from which this example is taken. But we'll keep moving right along. The key thing to note, of course, is that G3 is the final grade at the end that we're interested in predicting for this year's students. Okay, so this is a summary of what we do and don't know. From last year's students, we know their demographic information, their midterm grades, and their final grades. From this year's students, we know the demographic information and the midterm grade, the first midterm, which we're calling G1, grade 1. We don't know the final grade. That's the thing we're interested in knowing. So now we can more clearly say what we're going to do. And our procedure is that we're going to look for patterns in last year's data. We're going to predict final exam results for this year's students using only their demographic information and midterm grades, the two pieces of information we know. And then our ultimate goal, of course, is to then use that information, those predictions, to provide extra support to students who are at risk in this year's cohort. Okay, so this is another review. What we had before was we sorted spaghetti and water into two groups, spaghetti and water, and now we're using an analogous sorting mechanism to sort students in this year's cohort into group 1, which is students predicted to pass the class, and students at risk of failing the class. So this is another way to think about it. Now, before we can do what I just said, we have to train a machine learning model, which I've also been referring to as a sorting mechanism. So we're making this diagram gradually more complicated, and we're going to take the spreadsheet data from last year's students, which you just saw me display, create some kind of sorting mechanism, finalize that that mechanism actually is good at making these predictions. Then, once that's the case, we'll use that same sorting mechanism with this year's student data to sort this year's students into the two groups of students we think will pass and students we think may be at risk of failing. In order to calibrate the sorting mechanism inside of the computer, we need to first teach the computer something about the patterns and test whether we actually did a good job of making the filter before we trust it to actually give us any kind of prediction on the new students for this year. And so it's kind of a trick we play on the computer. We take 75% of the students from last year and we use them to make the sorting mechanism, the machine learning algorithm. We save 162 students, or 25%, randomly selected, which we call a testing data set. And then what we're going to do is we're going to trick the computer into thinking that this 162 students are actually new students who we want to make a prediction about. But in reality, since they're also from last year and we just hid them from the computer, we know what their results are. And so we can see how well did our predictive model work just by splitting up students from last year and using them for different purposes in this fashion. All right, so let's keep going. So as I said just now, we're going to give 75% of last year's data to the computer, and we're going to make what we're calling a decision tree. And this is what the computer makes when we give it those 487 students. It looks across all of the information we have about the students, right? So that's all of the information right here, everything other than the final grade, except for last year's students, which is here. And then what it does is it sees how can I divide the data to figure out what were the student results. And so what the computer did is it tried a lot of different combinations of decision trees, and then it settled on the best one, which is saying that, okay, if you start with these 487 students, you can create a breakpoint of 12 for their midterm grade, which is G1. If someone had a midterm grade less than 12, let's send them to the left. If they had a midterm grade greater than 12, let's send them to the right. So 229 people get sent to the right, 258 get sent to the left. Then it further divides the data using the first midterm grade of G1. And then it uses other variables to further subdivide the data until it gets down to this point at the very bottom, where it can classify all of the students into these different groups that you see at the very end here. Okay, and this is a list that the computer gives us of how important each of the variables, also called features, and again, those are just columns of data in the spreadsheet. How important is each of the columns of data? And what it's telling us is that the most important was the midterm grades. And then you can see a ranking of the next most important pieces of information in the data. And what this means is that if we were to use a decision tree to help us figure out who is likely to pass or fail for this year, we would only need to give the computer, say, these top 15 pieces of information. All of the other pieces of information were not very important to the decision tree, the ones you can see down here. And so we wouldn't even need to collect those this year. And so that's a way we can also make our analytics a little more efficient year after year. Okay, so now we made that decision tree. Now we need to see how good is it actually at making predictions on fresh data. And ultimately, we're going to use it to make predictions for this year's students, but we can't trust it to do that quite yet. We first want to see, can it make good predictions on those 162 or 25% of the students we left out before that you'll remember from a few minutes ago. So what you see on your screen now is only those 162 students who were left out of last year's data. And what I did is I put them through that decision tree that you just saw. And what we have here that you should focus on is two columns. G3 is that their actual grades that we secretly do know from last year, right? And then on this column to the right of that is the prediction that the decision tree made for all of these 162 people. So the decision tree only looked at the midterm grade and everything to the left, the demographic information. We hid the actual true answer, the final grade, from the computer. And then we are now able to compare how well did it make these predictions. So in red is when somebody failed in G3. And in red, in the prediction column, is when someone was predicted to fail. These are the predicted scores. And so what we can see is that in this case, row 7, this person's prediction was correct. It was off by about 1.6, but it still tells us this person who actually failed is also predicted by the model to fail. And so if this was this year's data, this student would have correctly been identified as an at-risk student. Now, if we go down a little bit more, we see here, this person is an example of someone who passed, although they barely passed, but the model predicted that they would fail. So this is someone to whom we might provide remedial support, but perhaps they didn't necessarily need it. or maybe since they're borderline, we did want to provide it. Now, this is what we consider to be the worst situation because this is somebody who scored a 6, they failed, but the model thought that they were going to score an 11. And so this is an example of someone who perhaps we wouldn't have realized is going to fail, but they actually would have failed. So this is sort of equivalent to when like a medical diagnostic test fails to detect someone who has a disease, so a false negative. So that can sometimes be dangerous. So this is the raw data view of the predictions made by the model, but this is a little bit messy. And so there's easier ways for us to visualize that. So we just did this. We looked at the video spreadsheet. And now this is an example of how we can look at our results in a simpler format. And so what we have here is what we call a confusion matrix. And it's an aggregate of the 4 types of people that can occur in the data with the predictions. So this is again out of those 162 students who were used to test the model. Out of those 162, there were 29 in this column who actually did fail the class. Out of those 29 who failed the class, 24 were predicted to fail correctly. 5 were predicted to actually pass, just like that one person I showed you who scored a 6 but was predicted as an 11. That was a mistake. These 5 people, the model couldn't figure out that they were going to fail. And then we have the sort of reverse here. These are people who actually passed in this column. And out of all the people who actually passed, the model thought that 12 of them would fail, so these are mistakes. And then it thought that 121 of them would pass, which were correct predictions. And that's what's summarized down here in these bullets. And one thing to note is that 10 was used as the cutoff between passing and failing for these rows, these predictions. But what we can do, so actually what we'll do next is look at a few metrics related to that. So these are some metrics we often calculate to see how well a machine learning predictive model was able to make predictions, how useful it is to us. And so there are 3 metrics. One is accuracy, which is the fraction of correct predictions divided by the total number of predictions that were made. So that was 89.5%. Then in our case, the number of students we would remediate. So we would provide remedial support to anyone who's predicted to fail. We wouldn't know whether they fell into this actually failed or actually passed category when we did it this year. And then finally, students who we could say fell through the cracks. We weren't able to help them even though they needed help. And that's this 5 people here. People who the model thought would pass, but actually they failed. Okay, so let's keep going and let's look at the same thing again, except what I did here is I went back to this data sheet and I said to the computer, hey, mark anyone in red, not only who's under 10, but anyone who's under 11.5. Let's make the test a little more sensitive. You could think of it in that sense. And what happens when we do that is that it predicts correctly everyone who failed, but then it makes a big mistake here. It thinks that 56 people are also going to fail who actually ended up passing. So what happens is our accuracy in that case goes way down to 65.4%. The number of students we have to remediate is absolutely massive because this is 85 out of just the 162 people who are in this data set that we're using to test. So about 50%. But the good news is nobody falls through the cracks. So we can do a side-by-side comparison here of all these matrix, and it's ultimately up to us which of these models we want to use, or if we even want to use any of them at all. And so what we would do next, after what I just showed you, is that we would take the model, and if the model didn't have metrics that we thought were good, then we wouldn't use it. And we would maybe try to make a different model, or we would say, okay, well, maybe we just won't use predictive analytics in this case. But if the model we made was good when we put those 162 students through it as a test. Then we could maybe feel comfortable using it to make some predictions about this year's cohort of students. And so what you see here in this table is an example of what those predictions might hypothetically look like. And what the computer would give us is just who all were predicted to fail and who all were predicted to pass. Since it's this year's students and they've only finished G1, the first midterm, at this point, we don't actually know the actual answers anymore. That's why it's really important that we trust our model when we look at those 162 testing students before we actually trust it on this year's students. So now we turn our attention to deciding what do we actually do with this analysis that we've just completed. And so I showed you two different confusion matrices, right, with different results. One thing you have to do is choose which of these is more useful to me. That's one thing that you can do. Another is to decide, well, do I use this at all in my work as perhaps an educational administrator would be an example of somebody using this. So what I would say is that you want to potentially consider using many sources of information to make decisions about what types of support to provide to students in this case. So you don't just want to look at these models, you want to use the results of these predictive models as one of many inputs into whatever action you're going to take and support you're going to provide to students. Another thing to think about is, remember, probably we wouldn't have as many resources as necessary to provide remedial support to 50% of our students, right? If we used the more loose cutoff at 11.5 that you saw the results of before. Um, but we perhaps would have enough resources to provide remedial support to all the students who would need it if we used the cutoff at 10. But then remember, 5 people would fall through the cracks. But maybe it's not a binary decision. Perhaps, for example, what you could do is you could warn everybody who is predicted to be at risk of failing at the 11.5 threshold. You could give them some kind of warning that, hey, we caught your case based on this predictive model, and just be aware that you're considered at risk in some sort of well-worded message to them. And then we could give extra attention to those who are predicted to fail at the threshold of 10. So there could be ways to adjust and reallocate our resources to still provide the support in the way we want it to. And the other consideration is that if you have so many people predicted to get below an 11.5, which is really close to failing the class, perhaps you'd also want to look more broadly at your program. So the analytic methods are not only to help you, identify at-risk students in this example, but also to help you provide, more systemic level information as well, if that's something that would be useful to you. So now we'll go back to the full analytics process again, just to review what we did. This is the same thing you saw before, and we just walked through basically every part of this, but I'll summarize it all again. But you could skip forward if you feel you understand it really well. So we divided last year's data into 75% of the students, which is 487 students, into a training data set. We kept 25% of the students, which is 162 people, still from last year. We kept them for later into what we call a testing data set. Then we trained a predictive machine learning model, which you can just think of as a fancy Colander filter that we're using as a sorting mechanism to classify something that we pour into it, which in this case is students. Then we've made a model. We go back to those 162 students we use as a testing data set, and we plug them into that same predictive model, which may not always be a decision tree. We plug them into that model, and we see, is the accuracy and other metrics that we care about, such as the ones we saw before, are those metrics good or bad? And if they're good, then you can report the result that, yes, we made a predictive model that's useful to us in our work, and then you can use it to make predictions, and then you can go to the red, which is our ultimate goal, which is to take new data, which is this year's students, for whom we only know their demographic information and their midterm grades. We don't know their final grade yet. That's why we're doing all of this. We plug those students into the same predictive model, and then it gives us predictions about those new students this year that we can use to take action, which in this case means providing some kind of remedial support to the students. Now, let's say we had tested the predictive model with these 162 people, but the accuracy was not sufficient and the other metrics were not such that we thought it would be useful to plug in the new data. Then we go back to the green track and we start over. So there are lots of different types of predictive models you can make, or you could simply decide not to use these methods if this approach isn't really going to help you, which is often the case. So again, I would encourage everyone to just think of this as a tool in your toolbox, not as the only tool or not as the one new thing that's going to happen across education necessarily. Okay, so before we end, I wanted to share quickly that we in the Health Professions Education Program at the Institute are actually working on a project very similar to the example you just saw. The example you just saw is a fully completed example that I'm now using for illustrative purposes, but we're actually halfway through a very similar procedure in partnership with our physician assistant program here at the Institute to work on taking their data from cohorts graduating in 2017 through 2019 and using that to see if we can create an early warning system for detecting students who may be at risk in the classes of 2020 and 2021 who are soon going to be taking their national certifying exam. So these methods can quickly and easily be applied, at least at the level described in this video, without necessarily too much additional effort, which is something that's really great about these methods. Also, one thing to note, the PA, the Physician Assistant Program, is a 2-year program here. Okay, and the next few slides are just notes that you can pause and read on your own. They're not anything we're going to necessarily go over, but if you'll be in class with me, then these are also things that we may discuss together. So I know this has a lot of words on it, but you can pause it. You can also open the slides at the link I showed before and make the font bigger. And this is where we'll end, some points to discuss. Thanks everyone for listening to this video. For those of you who I'll be in class with, I look forward to discussing a lot of these things and also answering any questions you might have. And also feel free to email me any questions you have in advance if you'd like.